All right, welcome to another deep dive where we, take some really cool math and kind of pick it apart and try to understand it a little better.
Yeah, that's right.
Today, we're going to be talking about something called self-complementary graphs. Number theory folks, you might remember the concept of a set complement.
Right.
You've got your universal set, and then you have a set within that, and the complement is everything that's not in that set.
Exactly.
And it's a very similar idea when we're talking about graphs in graph theory. So, graphs are made up of points called vertices and lines called edges, which connect those vertices.
Right.
And the complement of a graph is just the graph on the same set of vertices that has all the edges that the original graph doesn't have and doesn't have the edges that the original graph does have.
That's a good way to put it. Yeah, you're just flipping the connections, essentially.
Right. So if two vertices are connected by an edge in the original graph, then they're not connected by an edge in the complement and vice versa.
Right, on the same set of points.
Yeah. Right. Exactly. So you can think about it as just taking all the edges, erasing them, and then drawing in all the edges that weren't there before.
Mm-hmm.
So that's the complement of a graph. And that brings us to our topic for today, which is self-complementary graphs. So self-complementary graphs are graphs that are isomorphic to their own complement. Now, isomorphic is a fancy word that just means structurally the same.
Yeah, basically structurally identical.
Right. So if two graphs are isomorphic, it means that you can relabel the vertices of one graph to get the other graph.
Mm-hmm.
So if we have a self-complementary graph, it means that if we take its complement, we can relabel the vertices of the complement to get back the original graph.
Exactly.
Yeah.
So you take the complement, you relabel the vertices, and you've got the same graph back.
Right. And so these are really interesting graphs because they have a lot of cool properties and a lot of really interesting structure.
Right.
And we're going to be exploring this today through the lens of sequence A000171 in the OEIS, the Online Encyclopedia of Integer Sequences.
Yeah, the OEIS is a great place to look for these kind of patterns in math, and this sequence is a really neat one.
Yeah. So this sequence enumerates the number of self-complementary graphs with n vertices. So for example, the first term in the sequence is 1 because there's only one self-complementary graph with one vertex.
Right, because with only one vertex, there's only one graph you can make.
Exactly. The second term in the sequence is 0 because there are no self-complementary graphs with two vertices.
Right.
And so on and so forth. So the first few terms of the sequence are 1, 0, 1, 2, 0, 6, 10, 36, and so on.
And you see all those zeros in there, right? That's pretty interesting.
Yeah, and that's kind of a hint that there's something going on here.
Yeah, there's some kind of constraint.
Right, it's not just any number of vertices that's going to work.
Exactly.
So let's start by talking about why there are no self-complementary graphs with two vertices. So if you have a graph with two vertices, there are only two possibilities. Either the two vertices are connected by an edge or they're not connected by an edge. And if they're connected by an edge, then the complement has no edges. And if they're not connected by an edge, then the complement has an edge.
Mm-hmm.
And so there's no way to relabel the vertices of one of those graphs to get the other graph.
Right. You can't relabel a graph with an edge to be a graph without an edge and vice versa.
Exactly. So that's why there are no self-complementary graphs with two vertices.
Yeah.
And a very similar argument can be made for three vertices.
Yeah, basically. Because you can have 0 edges or 1 edge or 2 edges or 3 edges, and the complement will have the opposite number of edges.
Right. And there's no way to relabel those to get the other.
Mm-hmm.
So now let's talk about n is 4. So the sequence tells us that there's one self-complementary graph with 4 vertices, and it turns out that this graph is what's called a path graph.
Yeah.
So a path graph is just a graph where the vertices are all in a line, and each vertex is connected to the vertex next to it.
Right, just like a straight path.
Right. So for example, if we have vertices A, B, C, and D, then a path graph would be A connected to B, B connected to C, and C connected to D.
Right.
And the complement of this graph would be the graph with edges connecting A to C, A to D, and B to D.
Mm-hmm.
And it turns out that these two graphs are isomorphic to each other. You can relabel the vertices of one graph to get the other graph.
Yeah, the complement is also a path graph.
Yeah.
You just have to relabel the vertices correctly.
Exactly. And now let's talk about N5. So the sequence tells us that there are two self-complementary graphs with 5 vertices.
Okay.
And one of these graphs is a cycle graph. So a cycle graph is just a graph where the vertices are all in a circle and each vertex is connected to the two vertices next to it.
Right, like a pentagon in this case.
Right. So for example, if we have vertices A, B, C, D, and E, then a cycle graph would be A connected to B, B connected to C, C connected to D, D connected to E, and E connected to A.
Right.
And the complement of this graph would be the graph with edges connecting A to C, A to D, B to D, B to E, and C to E.
Mm-hmm.
And it turns out that these two graphs are isomorphic to each other.
Right. Again, the complement is just another cycle graph.
Exactly. So that's one of the two self-complementary graphs with 5 vertices. The other one is a little bit more complicated, but it basically has kind of a central vertex and then 2 pairs of vertices that are connected to that central vertex and to each other.
Mm-hmm.
So those are the two self-complementary graphs with 5 vertices, and then we get to n6 and n equals 7.
Mm-hmm.
And the sequence tells us that there are no self-complementary graphs with 6 or 7 vertices.
Right. More of those zeros popping up.
Right. So it seems like maybe there's something going on here with the number of vertices.
Yeah, it looks like there might be a pattern there.
Right. So it turns out that there's a really important property of self-complementary graphs that explains why this is the case.
Okay.
So a self-complementary graph with n vertices must have exactly n times n minus 1 divided by 4 edges.
Interesting. Why is that?
Well, so the total number of edges in a complete graph with n vertices is n times n minus 1 divided by 2.
Right.
And if a graph is self-complementary, it means that it has the same number of edges as its complement. And together, the graph and its complement have all the edges of the complete graph.
Right, because if an edge isn't in the original graph, it has to be in the complement.
Exactly. So the graph and its complement split the edges of the complete graph evenly.
So each of them has to have half the number of edges of the complete graph.
Exactly. And that means that each of them has to have n times n minus 1 divided by 4 edges.
Right, that makes sense.
And so this explains why there are no self-complementary graphs with 6 or 7 vertices.
How so?
Well, because if you plug in 6 or 7 for n into this formula, you don't get a whole number.
Ah.
Right. So for 6, you get 6 times 5 divided by 4, which is 152. And for 7, you get 7 times 6 divided by 4, which is 212.
Right, and you can't have half an edge.
Exactly. So that means that there are no self-complementary graphs with 6 or 7 vertices.
Interesting. So is this formula like a rule? Does it mean that if n times n minus 1 divided by 4 is a whole number, then there must be a self-complementary graph with n vertices?
That's a great question, and unfortunately, it's not quite that simple. So it turns out that this formula is a necessary condition for a self-complementary graph to exist. Meaning, if a graph is self-complementary, then this formula has to hold, but it's not a sufficient condition. So just because the formula holds for some value of n, it doesn't guarantee that there actually exists a self-complementary graph with that many vertices.
Ah, okay. So there could be other reasons why a self-complementary graph doesn't exist, even if the number of edges works out.
Exactly. There are a few other interesting properties of self-complementary graphs that are worth mentioning. So, for example, a self-complementary graph with more than one vertex has to have a diameter of either 2 or 3.
Okay, now what's diameter again? Remind me.
Right. So diameter is the longest, shortest path between any 2 vertices in the graph. So you take every pair of vertices, you find the shortest path between them, and then you take the longest of those paths, and that's the diameter of the graph.
Okay, got it. So the longest, shortest path can only be 2 or 3 steps long in a self-complementary graph.
Right, if it has more than one vertex. Yeah.
That's interesting. Why is that?
Well, it kind of has to do with the fact that the graph is isomorphic to its complement, right? So if a graph has a diameter of 1, it means that every pair of vertices is connected by an edge.
Right, that would be a complete graph.
Exactly. And the complement of a complete graph has no edges.
Right.
And so the only way that a graph with a diameter of 1 can be isomorphic to its complement is if it only has one vertex.
Makes sense. What about diameters larger than 3? Why can't those happen?
Well, if a graph has a diameter of 4 or more, it means that there are pairs of vertices that are quite far apart in the original graph, right?
Yeah.
But when you take the complement, those vertices that were far apart are going to become close together.
Ah, I see. Because the edges that weren't there are now there.
Exactly. And so the diameter of the complement is going to be much smaller than the diameter of the original graph.
So they can't be isomorphic because their diameters are different.
Exactly. So that's why a self-complementary graph with more than one vertex has to have a diameter of either 2 or 3.
Okay, cool. That makes sense.
So now let's talk about some specific examples of families of self-complementary graphs.
Okay.
One really cool family of self-complementary graphs are the Paley graphs.
Ah, Paley graphs. Yeah, those are really neat.
Yeah. So Paley graphs are constructed using finite fields and quadratic residues.
Right, so you start with a prime power Q that's congruent to 1 modulo 4,
Mm-hmm.
and then the vertices of the Paley graph are the elements of the finite field with Q elements.
Okay.
And then two vertices are connected by an edge if and only if their difference is a quadratic residue modulo Q.
Right. And so it turns out that all Paley graphs are self-complementary.
Yeah, that's a pretty neat result.
It is. And there's a really cool example of a Paley graph that's also a Rook's graph.
Oh, yeah?
Yeah, so the 3 by 3 Rook's graph is actually the Paley graph of order 9.
Interesting. So you can think about it like a chessboard, but it's a 3 by 3 chessboard, and a rook can move horizontally or vertically to any square on the board.
Right. And so the vertices of the graph are the squares on the chessboard, and two vertices are connected by an edge if and only if a rook can move from one square to the other in a single move.
And that turns out to be self-complementary.
Yeah, it does, and it's because of the symmetry of the chessboard.
Right. So if a rook can move from square A to square B, then it can also move from square B to square A.
Exactly. And so that means that the graph and its complement have to have the same structure.
Cool. So that's the Paley graphs. Are there other families of self-complementary graphs?
Yeah, there are. But the Paley graphs are kind of a special case because they're constructed using number theory.
Right. Most other families are constructed using other techniques.
Exactly. But it's worth mentioning that there's also an infinite self-complementary graph called the Rado graph.
Ah, the Rado graph. Yeah, that's a pretty wild one.
It is. But we won't go into too much detail about that here because it's a little bit beyond the scope of this deep dive.
Right.
So now let's talk a little bit about the computational complexity of determining whether a graph is self-complementary.
Okay.
So it turns out that this problem is computationally equivalent to the graph isomorphism problem.
Right, which is a classic problem in computer science.
Exactly. And so that means that it's not known whether there's an efficient algorithm for determining whether a graph is self-complementary.
So there might be, but we haven't found one yet.
Right. And it also means that it's possible that this problem is NP-complete.
Which would mean that it's really hard to solve for large graphs.
Exactly. So now let's go back to the OEIS sequence, A000171, and talk about some of the formulas that are given there.
Okay.
So one of the formulas says that A4n equals A003086-2n,
Yeah.
where A003086 is the number of degree sequences of graphs with 2n labeled vertices.
Okay, now remind me what a degree sequence is again.
Right, so a degree sequence is just a list of the degrees of the vertices in a graph.
Okay, and the degree of a vertex is the number of edges that are connected to it.
Exactly. So for example, if we have a graph with 4 vertices, and the degrees of those vertices are 1, 2, 2, and 3, then the degree sequence of that graph would be 1, 2, 2, 3.
Okay, got it. So what's this formula telling us about self-complementary graph then?
Well, it's telling us that the number of self-complementary graphs with 4n vertices is equal to the number of degree sequences of graphs with 2n labeled vertices.
Interesting. What kind of connection is there between those two things?
Well, that's a good question. It's not immediately obvious why those two things should be related.
Right.
But it's a really cool result, and it suggests that there might be some deeper connection between the structure of self-complementary graphs and the degrees of the vertices in those graphs.
So the degree sequence of a smaller graph somehow influences the self-complementary property on a larger scale.
Yeah, exactly. So another formula that's given in the OEIS entry is a 4n plus 1, A047832. And this formula says that the number of self-complementary graphs with 4n plus 1 vertices is equal to the number of self-complementary tournaments on n labeled vertices.
Okay, now what's a self-complementary tournament?
So a tournament is a directed graph where every pair of distinct vertices has exactly one directed edge.
Like a round-robin sports tournament where every team plays every other team once and one team wins and one team loses.
Exactly. And a self-complementary tournament is just a tournament that's isomorphic to its complement.
I see. So this formula says that self-complementary graphs with a certain number of vertices are somehow related to self-complementary tournaments with a smaller number of vertices.
Right. And again, it's not immediately obvious why those two things should be related. But it's a really cool result, and it suggests that there might be some deeper connection between self-complementary graphs and self-complementary tournaments.
Yeah. Maybe there's a way to take a self-complementary tournament and turn it into a self-complementary graph, or vice versa.
Yeah, exactly. And then finally, the OEIS entry gives the formula AN, A007869, and A054960N,
Okay.
where A07869N is the number of unlabeled graphs with n nodes and an even number of edges, and A054960N is the number of unlabeled graphs with n nodes and an odd number of edges.
Okay. That seems to relate the number of self-complementary graphs to the difference in how many graphs have an even versus an odd number of edges.
Right, and this formula is actually really intuitive if you think about it.
Okay, how so?
Well, remember that a self-complementary graph with n vertices has to have exactly n times n minus 1 divided by 4 edges.
Right, we talked about that earlier.
And that number is either even or odd. And so what this formula is saying is that the number of self-complementary graphs is basically the difference between the number of graphs with an even number of edges and the number of graphs with an odd number of edges.
Ah, I see. Because the self-complementary property fixes the parity of the number of edges, so it has to be related to this overall difference in how many graphs have an even versus an odd number.
Exactly. So those are just a few of the really interesting formulas that are given in the OEIS entry for sequence A000171.
Yeah, that's really neat.
And there are a lot of other cool things that you can find in that entry if you're interested in learning more about self-complementary graphs.
I'll definitely have to check it out. Thanks for the recommendation.
Yeah, no problem. So for our number theory students who are listening, I just wanted to leave you with a final thought to kind of ponder.
Okay.
So we've seen that the number theoretic properties of n, specifically its residue modulo 4, are really important for determining whether a self-complementary graph can exist.
Right, that's the whole reason why we have all those zeros in the sequence.
Exactly. But I think it's really interesting to think about how those number theoretic properties might not just permit or forbid the existence of self-complementary graphs, but actually dictate the possible structures of those graphs.
Okay, so like maybe the prime factorization of n, or whether n is a perfect square or not, could somehow influence the way that the vertices are connected in a self-complementary graph.
Exactly. And I think it would also be really interesting to think about whether there are any deeper algebraic structures underlying these enumerations.
Right, like maybe there's some group theory or ring theory going on behind the scenes that connects the arithmetic properties of n to the structure of these graphs.
Yeah, exactly. So those are just some things to think about. And I would encourage you to explore the references that are provided in the OEIS entry and the related sequences if you're interested in learning more.
Great advice. This has been a really fascinating discussion. I've learned a lot about self-complementary graphs today.
Yeah, me too. Thanks for joining me.
Of course, it was a pleasure.
All right, well, that's all the time we have for today. Thanks for listening, and we'll see you next time.
See you there.